First of all, I want to acknowledge uh, for acknowledge uh, the committee for inviting me for this nice workshop. Uh, I'm going to present this work, which is in archive. It was done in collaboration with Herman Freire and Rodrigo Pereira. But first of all, I want to talk about this model. It's a Kitaev Condoleezza model. It was the first model when I came to Unicamp to do my postdoc with Eduardo. He proposed this work. Nevertheless, it was the last work that we did together. It was published some time ago. It was this one, 2021. But it's nice work because it gave some ideas for other projects. We have this type of bilayer structure, and here in the first honeycomb lattice, we have a Kitaev spin system described by this Kitaev model, which I'm going to talk about in the few slides. And we have this conduction electrons, and the interaction between the two systems is given by this Kondo interaction. And what we did was to investigate the properties of this model, use this kind of representation. We have to imagine this kind of fractionalization where the spin half operator is written in terms of Majorana operators, the Cj for each site. And you have to decouple this Kondo interaction by means of this order parameter, which gives some kind of pairing between the conduction electrons and the Majorana fermion, and it has a staggered phase. Nevertheless, it's possible to study this model at the mean field level, and we found something interesting. For example, we have this kind of antichiral mode, which is due to the presence of a Bogoliubov firm surface in the system, and there is a transition from a fractionalized firm liquid to a superconducting phase. And most important, the superconducting phase is described in terms of this odd frequency pairing. It's quite interesting because besides this property of the order parameter, it has some kind of pairedness wave feature, which means that the center of the Cooper pair has a finite wave factor. And I want to thank you, Eduardo, for all the time at Unicamp and for the nice advice and for everything. I never call you Dudu, but it's a nickname. It's a nickname of Eduardo. So after that, I'm going to present my work, the work of the title. So the outline of my work is this one. In the first part, I'm going to talk about the Kitaev spin liquid and how it can describe some modulators. And then I'm going to move on to discuss bond directional multipolar interaction between higher multipolar moments, especially this case when I have this kind of the J, which is the size of the multipolar moment is equal to 3/2. Then I move on to discuss a solvable model for this kind of system. And then I'm going to talk about the stability of this multipolar, spin liquid, which will show up in the exact fashion. And then I'm going to close with the summary of my work. So to begin with, the Kitaev spin liquid is described by this model. So we have a honeycomb lattice, and for each bond of the honeycomb lattice, we have some kind of Eisen interaction between the dipolar operators. So it's a model for spin half operators, but it's a toy model which was designed by Kitaev just in the context of topological field theory, not for condensed matter. But it was soon realized by this duo of physicists that in a modulator in which the transition matter has a 4D or 5D electronic configuration, when this system is subjected to a crystal electron field and then spin-orbit coupling, we can obtain this kind of interaction, this bond-dependent interaction, and of course, we have to include the electronic correlation, we ended up with this kind of Hamiltonian. And this Hamiltonian can be solved in terms of Majorana operator. It's here we have use 4 Majorana operator actually. Kitaev uses this kind of representation to solve the model and have this kind of fractionalization, where the B's are the, in this case, the gauge Majorana operators, and the C is the matter Majorana operators. And using this kind of representation, it's possible to show that the system will have this exact solution. We can diagonalize the Kitaev Hamiltonian for the honeycomb lattice and obtain this kind of dispersions for the system. And we can have a gapped spin liquid or a gapless spin liquid. In the case of when we have a gapless spin liquid, we have this kind of Dirac cones. So the question is it possible to realize this kind of Hamiltonian? And there are some kind of proposal, and the system, the ruthenium chlorine 3 is the most known system for realize the Kitaev spin liquid. Actually, the system exhibits this kind of zigzag order in the honeycomb lattice, and there is this claim that there will be some kind of spin liquid physics when the magnetic phase is destroyed by a magnetic field. And there is a regime, a finite regime of magnetic fields, where, for example, the thermal Hall conductance will exhibit this kind of behavior. There is the claim is that it is constant, that the thermal Hall conductance for this kind of in-plane magnetic fields, and the kind of behavior exhibited by this function is the same predicted for the Kitaev spin liquid. So it is possible in that case. Actually, the claim is that this system will is the smoking gun for the existence of for the realization of the Kitaev model, and of course for the realization of Majorana fermions in a condensed matter context. Nevertheless, but I want to try to focus on other systems. And there are some kind of Kitaev-like behavior, not only in system described, but for spin equals half, but for other situations. And for example, system in which the magnetic moment has a larger value. For example, S equals 1, 3/2, and so on. And in that case, if we consider the uncoupling for the presence of uncoupling, it is possible to arrive at Kitaev Hamiltonian like in the case of the S equals half. So, but the downside is for this kind of generalization of the Kitaev model, it is not possible to find an exact solution. And the properties of the Kitaev model for this kind of generalization is obtained using numerical approach, for example, the MRG, exact diagonalization, and mean field approximations. So the question that I want to address is this one. Is it possible to obtain some kind of exact quantum spin liquid states for interacting systems in which the size of the magnetic of the multipolar moments, as you can say, is larger than half? And at the end, I'm going to give a positive answer. And we can start, for example, looking at these systems. In that case, systems modulators in which the transition matter has a D1 configuration. If we consider the presence of crystal electric field plus spin-off coupling, it is possible to obtain a low energy state described by J equals 3/2. And in that situation, we can have, besides the dipolar interaction, we can have quadrupolar interactions and octopolar interactions. And I'm gonna index, for example, the quadrupolar interaction by the irreducible representation of the octahedral group. So, for example, for the quadrupolar interaction, we have this gamma 3 irreducible representation. I'm gonna talk later about the role of these operators, but we have this gamma 3 representation, we have the gamma 5. Besides, for example, for this gamma 5 representation, I'm using this superscript X, Y, and Z, which refer to the bonds of the honeycomb lattice. And besides, I define this kind of operator, O tilde gamma, and the gamma here is using this kind of O3 and O2 quadrupolar operators. And gamma is, for example, gamma equals 1, refer to the X bond and so on. And in that situation, we can construct exact solvable model. Actually, we can use just the interactions which are allowed by symmetry. And we can define this quadrupolar Hamiltonian. And of course, we can use these interactions using just these quadrupolar operators. And it is possible to use, to define this kind of interaction. And the first interaction is, it could be generated integrating out the trigonal distortion, of course. And if we consider, for example, the limit in which this K quadrupolar prime interaction, which is due to this term, okay, here is 0, we cannot solve exactly this model. And the solution appear in this paper, which we published some time ago. Of course, Eduardo was involved in this project, but there is a solution using Majorana fermions, which I'm going to present in a few slides. And the solution just works if this K quadrupolar prime interactions is equals to 0. But now, yeah, of course.
I mean, these are, as you said, right, they are different reps, right?
Mm-hmm.
The O and the O tilde, right? So they can be different, and you can then if K of Q is much larger, can you just ignore the other sector just because it's a different rep? It's just going to renormalize that and just move on. I mean, does it need to be that stringent that KK prime has to be 0, identically 0?
No, it's not. It's just I'm playing with the interactions, and it cannot be 0. Actually, the interaction will be finite. I'm just playing with the limits of the model. It's a toy model. For the moment, I'm gonna set this interaction to 0, but at the end, I'm gonna include the interaction and study the model. So this is the model for the full model. This interaction is gonna give rise this type of ordering. There is a ferroquadrupolar vortex order. If I include the order interaction, the zero band model will disappear, but there is no multipolar spin liquid. So, but I can play a little bit with the order operators. For example, I can have this kind of octopolar operators for the same system, and you can label this operator for the irreducible representation. So we have, again, the gamma 5 and gamma 2 irreducible representation. And as I did before, I can construct multipolar models. In that case, using just this octopolar interaction. And for the gamma 5, I have the same kind of index X, Y, and Z refer to the bonds of the honeycomb lattice. And it is possible, this interaction is also allowed by symmetry. And most important, this kind of interaction appear in work for a hidden order used for describing this kind of heavy fermion. And if I throw away this interaction, this K octopolar prime interaction, I can solve the model. There is an exact solution, but once again, I have the zero bands, which is not good enough because I will ended up with a highly degenerate ground states. So the question, how can I get an exact solvable model with multipolar spin liquid ground states without this zero energy band? Oh, okay, there is a back. All right. And the answer is the following. I'm gonna using this full model, which is the sum of the quadrupolar octopolar interaction. And for the moment, I'm gonna throw away the k quadrupolar primed and k octopolar primed. So we have a model similar to the KTF models. We have this bond dependent interaction, involve the quadrupolar operators and the octopolar operators, but all operators is in the same gamma 5 reducible representation of the octahedral group. And in order to solve this, this model, you have to change the, actually have to write down these octopolar and quadrupolar octopolar operators in terms of pseudo-spin and pseudo-orbitals degrees of freedom. It's just a technical way. It's not important for understanding the solution. The important point is it is possible to write down these operators, the quadrupolar octopolar operators, in terms of pseudo-spin and pseudo-orbitals degrees of freedom. And if you look for the operators in the gamma 5 in reducible representation, it depends on S and tau. But for the O2, O3, and TXYZ, it depends only on the pseudo-orbital degrees of freedom. This is important. And using that, and once again, use the same kind of Majorana representation for the pseudo-spin, pseudo-orbital degrees of freedom, which Eduardo introduced me. That's an important point of Eduardo here. We can solve this model, and we can define the bond operators. Because of the Majorana representation you have completed, you have to define this kind of constraints. And also, the model has these plaquette operators defined for these sites. And the plaquette operator is important because it commutes with this Hamiltonian. So if this plaquette operator commutes with the Hamiltonian, the solution is given by the flux, gauge flux free of this operator, which square to 1. So the ground state is given by the eigenvalues of this plaquette operator, which is equal to the unit. So as did for the KTF model, we can solve, I'm not gonna show the dispersion, just the behavior of the dispersions. As you can see, there is no more zero energy band. So it works, the ground states, there is, doesn't have the highly degenerated feature shown before. And what else we can do? We have a system with an exact solution. We can break some of the symmetries of the model. And here, I just chose to break time reversal symmetry and the rotation symmetry using, for example, for the rotation symmetry, I'm considering strain fields, which are gonna couple to the O2 and O3 quadrupolar operators and breaking time reversal symmetry. And the magnetic field gonna couple to the TXYZ octopolar operator. And using this kind of this term, which I call delta HS, it commutes with the WP, the plaquette operator. So the solution, there is an exact solution. And when we solve the model and obtain the dispersions, most of the cases have a gapped system. But this feature sometimes appears, and actually the gap closes. And if the gap closes, it's maybe it's a signal of a quantum phase transition. And we investigated this kind of transition, just computing the Cherry number We have to evaluate the Berg curvature in terms of the Berg connection. And here is the phase diagram. For the charge number, we have a abelian phase with charge number equals 2, a non-abelian phase with charge number equals 1, and a trivial abelian phase with charge number equals 0. I'm considering just that the strain fields are the same. And of course, the system will realize 5 of the Kitaev 16-fold wave phase. The other phase with negative charge number is obtained if I consider negative magnetic fields. And this is, if I follow this line, and we can see that the Majorana-Book gap is going to close at the phase transitions, right? And of course, this can be further investigated if we calculate the spectrum of the system. Imagine a finite system with zigzag edges. And if I have a finite charge number, then the thermal Hall conductance is going to be finite. And in that case, is for the abelian phase, we have 2 chiral Majorana modes at the surface. So this, for the other case, we have just 1 chiral Majorana mode because the charge number is equal to 1. And for the trivial abelian phase, which show 0 charge number, we don't have a chiral mode. So came to the question that Rafael asked at the beginning. In the real life, we're gonna have, besides the exact solve model, you can have some interaction. The interaction are gonna break the integrability of the model. So if, for example, the K quadrupolar prime interaction is finite, we can have this kind of ferro-quadrupolar vortex order. If the K octopolar prime interaction is finite, we can have this anti-ferro octopolar order. Right. And in that situation, since we don't have an exact solution, we have to use some approximation method. In the weak coupling limit of the model, we can use midfield approximation, in which case I'm going to use a midfield order parameter for the anti-ferro octopolar order. This order parameter is going to break time reversal symmetry. And if I have a ferro quadrupolar order, I can describe this kind of order by this kind of double Q order parameter, which is going to break rotational and translational symmetry. I parameterize this order parameter in terms of amplitude parameter, which I call rho, and order parameter, phase order parameter, which I call phi. So using midfield approximation, I can evaluate the free energy of the model and minimize the free energy of the model. I obtain this kind of phase diagram. There is this multipolar spin-nickel phase, which is stable. If I increase the K octopolar prime interaction, I obtain this order, the anti-ferro octopolar order, in which the octopolar moment is going to behave like that. And if I increase the K quadrupolar, if I increase the K quadrupolar prime interaction, I obtain the ferro quadrupolar vortex order, and there is a regime in which we obtain both of these phases. So, and the transition between them is the first order. There is this kind of first order quantum phase transition between these, the two. And besides that, I look at the dispersions, and for the anti-ferro octopolar order, I have this semi-metallic behavior, and for the ferro quadrupolar vortex order, I have a gapped behavior, and for the coexistent phase, we have a metallic behavior between them. And this behavior can be explained by the symmetries that are broken in each one of the phase. Now, the other question that the other limit of this model that I investigated was the strong coupling limit of the model. In the strong coupling limit, it is not possible to use midfield approximation because the interactions, the K quadrupolar prime, K octopolar prime, are gonna excite the visons. So it's not possible to start from the multipolar spin-liquid phase. But if I consider for example, that the system is in the ferro-quadrupolar or anti-ferro-octopolar order, I can consider that the tau, for example, HI described the interaction that's gonna break the integrability of the system. And the HS is the Hamptonian which describes this multipolar spin liquid. So I consider that the system is frozen in one of these magnetic multipolar order, and then treat the multipolar spin liquid Hamptonian as a perturbation. So, and you have to understand when the system is going to be in the ferro-quadrupolar vortex or anti-ferro-octopolar order. And the transition between them can be obtained, just evaluate the energy. And on the left side, the system is going to be in the ferro-quadrupolar vortex order. And the right side, the system is going to be in the anti-ferro-octopolar order. And the transition is given by this interaction. K octopolar prime is equal to K quadrupolar prime over 2. So there is a first order transition. Then I can integrate out the pseudo-orbital degrees of freedom of this multipolar Hamptonian. And then the effective Hamptonian describes the effect of the multipolar spin liquid is going to be this one, which means that the system, the pseudo-orbital degrees, pseudo spin degrees of freedom, are going to be described by this Kitaev model, and the exchange interaction is going to are given by this dependence, in which we have to evaluate this correlation function involving the pseudo-orbital degrees of freedom. In that limit, we can calculate this correlation function using Holstein-Primakov transformation, and the result is this one. So this is the strong coupling phase diagram in which the system, for example, the system here is going to be in this anti-ferro-octopolar order for the pseudo orbital degrees of freedom, but the pseudo spin degrees of freedom will be described by Kitaev spin liquid, in which you have gapless excitations. On the other hand, if the system is in the ferro-quadrupolar vortex order, the pseudo-spin degrees of freedom are also described by a Kitaev spin liquid, but the excitations are gapped. So the difference between the strong coupling limit of the model, the weak coupling, is because we don't have the coexistence region between the states in which we have orbital multipolar order for the system. And this is the main result of this study. And with that, we have a summary of my work. I showed that bond directional interaction between quadrupolar and octopolar degrees of freedom can give rise to a multipolar spin liquid. And besides the multipolar spin liquid, you can have exact multipolar orders. And I showed that a strain magnetic field can play a key role to the emergence of topological phase with billion and nanobillion orders. And besides the system, of course, this multipolar spin liquid system, if we consider interaction that break the integrability, can give rise to ordered state, which is in the ferro quadrupolar vortex or anti-ferro octopolar order. But we also have on top of that state spin, hidden spin half Kitaev Hamiltonian. And that's it. Thank you.
So, open the questions.
So, Vanuildo, there's one thing that is confusing me. You are writing the Stevens operators for cubic symmetry.
Yeah.
But then you put this on a honeycomb system. So, isn't that going to end up splitting? Because, right, two of the Stevens will continue being a one two-dimensional representation. The other is going to actually join with the other one from another to the. So, isn't this an issue for?
Yeah, it could be an issue, but once again, I just was playing with the possibility of obtaining this kind of topological, non-trivial topological phase, and then you may be right regarding this, but it's just a toy model, and
No, I
we
understand.
want to investigate the.
I'm not
the
criticizing the
properties.
model. I'm just saying that since you know that there's going to be a crystal field term, you may want to see what the effect is. You can add that to your KO, right, and see what it does. I mean, it's certainly relevant, but well, actually, I don't know for the spin liquid. It may survive. So
Yeah.
it's a term that is unavoidable, and it may be worth taking a look. That's all.
Yeah, of course. And the model was, it was going, the model at some point was complicated, so I kept the minimum amount of parameters to play with. Yeah.
Yeah, thank you very much for this nice talk. I also have a question about the model that you work with. So
About?
the model that you are working with, I understand that this is a toy model, but what is motivating for dropping the dipole terms? You take into account quadrupole, and octopole, or like partly those, but you drop the dipole.
Yeah, the dipole interaction is because if I kept the dipole interaction plus quadrupole interactions, octopole interaction, I don't solve the mod exactly. So I threw away, of course, this dipole.
The original Kitaev type of anisotropy.
Sorry.
The spin.
Yeah, the motivation is once again, I just want to solve exactly a model for describing this kind of multipolar spin liquid. I know that the interaction, there are much more interactions that are important, and I didn't put in the original model. It's just to prove, to have a proof of principle of the existence of a multipolar spin liquid. But I have to consider all the interactions and just to.
I'm also asking because then you have a magnetic field, right, that couples to your octopole, and that would also couple to your dipole, I think. And that would be probably a stronger.
Yeah.
Effect.
Of course, there are limitations, and for the magnetic field, for example, the magnetic field coupled with the dipole interaction, but I didn't consider. Just there. Actually, in the limit of a small magnetic field, maybe I can have this kind of the TXYZ octopole interaction. If I start for perturbation limit, I can have this kind of interaction.
Okay, more questions? So if not, let's thank Vanuildo again.
Thank you.
My job is done.
Well done. Okay, closing remarks. We're finally here. Thank you all for coming. And well, my first thanks is for Jandira, which without her, nothing would be like this easy for us. And she's very efficient, very, very careful. Please, let's thank Jandira. And also the informatic guys, William and Luis. Without them, well, we had many problems in the computers. Thank you all. I would like to thank the Institute, IFT, for hosting us. It's mainly a high-energy institute, but they are very open to condensed matter, so they are starting it, and that's why we're here. We are on the few workshops on condensed matter physics. If you wish to organize things here, Jandira is here, so she'll make your life very easy. So thanks, IFT, and for this here is the South America branch of ICTP. So thanks for them. Probably you're gonna all receive some questionnaire for feedback, which will come from, I don't know, Elisa or Jandira. And please answer those questions kindly and carefully, so we can improve how to organize things here. If you have suggestions, please send to my email, and compliments, of course. If you have criticism, you can contact Vitor and Eric, so you can improve for the next time. Eric and Vitor, is very easy to organize things with you, and you guys are great. And it's very easy to organize things for a crowd like you. You guys did all the job of putting this very exciting scientific program. It's not me, I just put you together, you do the rest. Or me, or the organizer, I mean. So thanks you all for coming, and I hope we can, I don't know, do another one 2 or 3 years from now. I know coming to Brazil is hard, it's far away, but you see the good things that we have here. So I hope this will make you very happy to come back and present your new developments, and keep going. Happy birthday, Eduardo, in October. And that's it. Have a safe trip back.